basic output parameters of a centrifugal pump. A centrifugal pump was shown in this picture. Assuming a steady flow, the pump basically increases the Bernoulli head of the flow between point 1 and the A of the pump, as shown also in this picture, and point 2, neglecting viscous work and head transfer. These changes denoted by H. At point 2 minus the energy, specific energy back, point 2, point 1, which is also equals to the HS minus HF shaft head and friction head. Where HS is the pump head supplied and HF the lucid, excuse me, in this supplied head and friction HS and friction. The net head H is a primary output parameter for any turbo machines. Since this equation is for the incompressible flow, it must be modified for gas compressors with large density change. Usually V2 and V second and V1 are about the same. Z second and Z1 is no more than a meter or so, and the net pump head is essentially equals to the change in pressure head. So we can neglect it. Or the difference, and also for a pump, not for a line. Now we can write the head of the pump as the pressure change of the output and outlet and inlet fluid. The power delivered the fluid simply equals the specific weight times the discharge times the net charge, the net head change. The power delivered to the fluid This is traditionally called the water horsepower. The power required to drive the pump is the brake horsepower. To drive the pump is the brake horsepower. And can be calculated from this relation. Where omega is the shaft angular velocity and T the shaft torque. If there were no losses, P, W and the brake horsepower would be equal, but of course P, W is actually less and the efficiency eta of the pump are defined as we had OG QH4 and BHP brake horsepower eta as efficiency equals to the OGQH on the shaft angular velocity multiplied the shaft torque. The chief aim of the pump designer is to make eta as high as possible over a broad range of discharge Q as possible. The efficiency is basically composed of three parts. Hydraulic and the mechanical volumetric hydraulic and mechanical. The volumetric efficiency eta V where QL is the loss of flow due to leakage in the impeller casing clearance. The hydraulic efficiency is the loss of liquid or fluid due to leakage of the impeller casing. Clearance. Eta, the hydraulic efficiency is eta H HS, where HF has 3 parts. Shock loose at the A due to imperfect match between, let me write it there. So we have eta V equals to the volumetric performance and eta hydraulic, where HF loose of shock loose at the A due to imperfect match between inlet flow and the blade. Friction losses in the blade passage and circulation loss due to imperfect match at the exit. Side of the blade. Finally, the mechanical efficiency is eta mechanical, the brake powerhouse, where PF is the power loss due to mechanical friction. Is the power loss due to mechanical friction in the bearing. packaging glands, other contact point. By definition, the total efficiency is simply the product of its three parts: volumetric, hydraulic, and the mechanical. All three parts are important and should be considered in the pump design. Elementary pump theory will be discussed in the next video part.